video we will move forward with covalent bond. In the previous video we have learned about the molecular approach, modern approach. Now we learn the covalent bond. First rule that you should remember is that covalent bonds are formed by the overlapping of covalent bonds are formed by the overlapping of half-filled atomic orbitals. Half-filled atomic orbitals present in the valence shell of the atoms. Okay, so if we analyze these statements, covalent bonds are formed by the overlapping of half-filled atomic orbitals present in the valence shell of the atoms. This means that, suppose for example, let us take an example of fluorine molecule, F2 molecule. Okay. So if you see the electronic configuration of F, it is 1s2, 2s2, 1s2, 2s2, 2p, 5. So this is the electronic configuration of fluorine. So if I draw it orbital wise, 1s2, 2s2, right? In this way we fulfill 2p5. Okay, so now let us imagine another one. So it will be also 1s2, 2s2, 2p5. So 1s2, 2s2, 2p5. Right? So we got we get this idea. Now what will happen? There, this spin and this spin, when you draw, just draw the opposite. Because remember that when these two F atoms will come closer to each other, what will happen is 1s2 will not take part in bonding. This is the valence shell. Second shell is the valence shell, in which there are S and P subshells. Okay, and in the P subshell, this is suppose Px, suppose this is also Px, this is suppose Py, this is also Py, suppose this is Pz and this is Pz. Then what will happen? It will look like this: 1s2, now suppose this is your 2px orbital, this is 2py orbital, suppose 2pz orbital, this is the 1s2 orbital. Okay, here 2px2, 2py2, 2pz is 1, yes or no? So here you can see 2px2, 2py2 and 2pz is 1. So you draw another fluorine molecule. Okay, sorry, I'm so sorry, I think it was not focused. Here is the fluorine molecule. Suppose I'm so sorry. Okay, suppose a C from here again, 2px2, 2py2, 2pz1. So here I have drawn, suppose this is the 1s orbital, this is 2px2, this is 2py2, and suppose this is 2pz1. This is the suppose x-axis, this is suppose the y-axis, this is suppose the z-axis. Okay, so now you take another fluorine molecule, which will be again, this will be 1s2, so this will be your 2px2, suppose here two orbitals are there, and 2py2, 2pz will overlap. Here when two fluorine molecules are coming close to each other, then they z 2pz molecule to 2pz. When p orbitals overlap, they overlap in this way. Okay, so they overlap in this way. This is orbital overlap of p. So does that mean that only P and P only overlaps, S and S only overlaps like we have seen in hydrogen? Yeah, P and S also overlaps. It will be like this. If this is P orbital, this is your S orbital. This overlapping can be there. That is not a big deal. Suppose, for example, it happens in methane. Okay, that you will, this you will see P and S overlap is also. But remember that P overlaps if Px is there, then it has to overlap with Px. Sir, why is so? Because both will have the same axis. Okay, and if Px overlaps with Px axis wise, then overlapping will look like this. Okay, this is what I want you to understand. If S orbital overlaps S, it will be like this, S and S overlap. So that is the basic funda that we have to understand. But when we show the bonding, suppose you have written fluorine ka 1s2 2s2 and 2px2 2py2 this and this. So 1s2 this is one F molecule, this is another F molecule, 1s2 2s2 2px2 2py2 2pz1. They will overlap. We will show the overlapping in this way. Okay, so that will give rise to your. Okay, so this is how bonding is done. So I hope that you are being able to understand or visualize the bonding. Here Z also orbital, or maybe sir, is it so that only PZ and PZ will only overlap? Can it not be PX and PX orbital? Yes. Can it not be PY and PY orbital? Yes, it can be. Okay, it can be both PX and PX orbital. It just depends on which orbital is this. This type. This diagram is correct. This type of overlapping will be there. So I hope that you have understood that what I have tried to say here. Okay, so this is the basic funda that I have tried to say. So always see that covalent bonds are formed by the overlapping of half-filled atomic orbitals present in the valence shell of the atoms. So this is what I wanted to, this point is what I wanted to explain. Okay, let us go into the second point. So second point is the orbitals undergoing overlapping must have electrons with opposite spins. The orbitals undergoing overlapping must have half-filled orbitals with opposite spin of electrons, and this is because of reason of this is Pauli's exclusion principle. Yes. Okay, so this is because of Pauli's exclusion principle. So I hope that you have understood. Another point that you should understand is that here also I have shown you that there is opposite spin. There should be opposite spin for overlapping. Here also I have shown you there should be so there should be opposite spin of the things. Okay, so this is the point that you should keep. Third point that you should keep in mind is that overlapping of atomic orbitals results in the decrease of energy and formation of covalent bond. Overlapping of atomic orbitals causes the decrease in energy, causes the decrease in energy and formation of covalent bond. Formation of covalent bond. So that also you should keep in mind. That yes, obviously, because if there is an atomic orbital, suppose, and if there is another atomic orbital, suppose. Now suppose this orbital is half filled or having only one electron, and this orbital is half filled only having one electron. Now what happens is that this space is quantum mechanically, this orbital space is quantum mechanically is in such a just hold on. Where is everyone? Oh, sorry. So this space or orbital space is quantum mechanically is such a space where if it has one electron cloud or if it has two opposite electron cloud, then it will be more stabilized. They are more quantum mechanically stabilized. Okay, so that's why overlapping leads to lowering of energy. If anyone asks that why is it so that overlapping of atomic orbitals causes decrease of energy and formation of covalent bond, the reason is that you see, because you can say because of this forces that they exist, attractive forces and repulsive forces, they overlapping, there is an extent of overlapping. Too much overlapping is also not possible, because you have learned here that if they go too much nearer to themselves, then there will be repulsion and hence the energy will increase. So there should remain a particular internuclear distance, a particular bond energy should be there. Okay, a particular internuclear distance and a particular bond energy should be there to must have so that it must have the lowest energy. Repeating my point. So this is what you have to understand, that okay, at a certain distance the overlapping occurs. Too much of overlapping is also not energy lowering process. So a certain extent of overlapping lowers the energy and hence formation of covalent bond is there. But however, at that certain range, the extent of overlap, number 4, remember, the extent of overlap determines the strength of the bond. Obviously, what is the reason behind this? If there is more extent of overlap, more extensive overlap is there, then suppose for example this is a 2p orbital, this is another 2p orbital. 2p orbital is smaller. Suppose there is 3p orbital and there is another 3p orbital which are bigger. So in that case the extent of overlap is small. In case of 2p the extent of overlap is greater because the orbitals are smaller. If you overlap 1s with a 1s, they both are small and the extent of overlap is more. But if you overlap a 3s with a 3s, okay, then the extent of overlap will not be more because they are bigger orbitals. Okay, so remember, the smaller orbitals have more extent of overlap and hence the length of the bond is also small. This you have learned in class 10 also, that the smaller the molecules, suppose hydrogen bonded to hydrogen, it is very strong bond, and bigger the molecule, chlorine bonded to chlorine, it is I think it is still small. Suppose carbon bonded to carbon, bigger it is, then the larger the length, easier to break the bond. Larger a stick, easier to break it. Smaller a stick, tougher to break it. So in that way, extent of overlap is more, then it comes closer, and the bond length, if the extent of overlap is more, what will happen is, I'll show you. If the extent of overlap is more, so this will come more down and there will be much more lowering of energy and hence more stable. Okay, see, just I'll compare the graphs. Suppose here, and the extent of overlap is such that it is like this here. Okay, and in another molecule the extent of overlap is little bit less. So when the extent of overlap will be less, it will go up like this because the extent of overlap is less. So that, see, deep in the energy, here the loss of energy is the energy loss of the bond energy. This is the bond energy, right? The bond energy is less, the bond energy is release bond energy. So the stronger the bond will be, the less stronger the bond will be, because smaller it is, the extent of overlap is more, and larger it is, the extent of overlap is less. So the more the extent of overlap, more lowering of energy will be there, and hence more stronger the bond will be.